Oh, I love going to the dentist. 3 hours of sleep. Yay. Yeah, I can't wait for that algebra test. These are all examples of sarcasm, and you had no problem in spotting it, aided by your common sense and the intonation I used. But what if you want to be sarcastic online? Wouldn't the lack of paralinguistic cues cause confusion? What triggers the sarcastic intent in written text? This question is largely addressed in my project entitled Detecting Sarcasm on Twitter. 3 main models were developed, from which we will discuss the statistical and the deep learning experiment. Each of them follows the same sequence of steps. First, the corpus is obtained and pre-processed. Second, we prepare the input, then we feed it to the trainer. Lastly, the model is evaluated and results collected. Let's have a look at the discrete features using the statistical model and analyze some sarcastic examples. We begin by observing some very basic indicators such as punctuation marks, user mentions, hashtags, and emojis, while also counting present intensifiers and interjections. As you can see, all of these were directly extracted from text and are called pragmatic features. Next, we obtain lexical information by collecting the individual words in each tweet. These are called unigrams. We apply the exact same technique to part-of-speech tags. We also identify the positive, negative, and neutral words, as well as a polarity score for the whole tweet. As you can see, there are words of different polarities inside the same tweet. This is called sentiment incongruity, and it lies at the heart of sarcasm. Observing that people are inclined to be more sarcastic towards specific subjects, such as weather or work, we build a topic model to extract these. Suppose that you have identified 6 main topics among your data. Then each tweet will be a mixture of them, and we use their share of topics as features. Finally, the most similar pair of words, as well as the most dissimilar pairs, are recorded. These will help us determine the context incongruities of a sentence. Having selected the features, we can now feed them to our trainer, which is a support vector machine, and obtain some useful results, which will be shown later. Let's move to the deep learning model, specifically to the input preparation step. Somehow, we need to represent our words numerically. One way to do this is by vectors with all 0 values except for the position uniquely marking a certain word with a 1. This is called one-hot encoding. While convenient, this method has 2 main disadvantages. First, each word vector is as long as the vocabulary, making it sparse and inefficient. Second, this representation does not keep any information about the relationship between words. A better way is to use dense vectors of continuous values, called embeddings, solving both of our problems. In this way, we can join all our word vectors to form a matrix that is fed to the trainer, finishing the input preparation stage. Now, we can move to analyzing the trainer, a deep neural network. Let's break it into the details. Here is a very simple neural network. It has some inputs and some outputs, as well as some connection between its units. It is organized in layers. Because their number varies dramatically across different architectures, we will abstract their details by a box. Stacking many such layers on top of each other gives birth to deep neural networks. These are the ones we use in this project. Specifically, we're interested in recurrent neural networks. If we establish that a simple network looks like this, taking some input x and outputting a vector a, this is how we depict a recurrent neural network. The loop indicates the recurrence, meaning that the network is repeatedly used over time in a sequential manner. Less ambiguously, the loop can be unrolled, with information being passed from one step to the next. A specialized type of recurrent neural network was employed in this project. It's called long short-term memory. Let's have a look inside its unit box. The central most important component of an LSTM unit is its memory cell, C, containing information that can only be updated by some structures called gates. As you can see, there are 3 gates. The input gate decides which parts of the previous memory cell will be updated, while the forget gate establishes which parts should be thrown away. The output gate focuses on what should be passed over to the next cell. By doing this at every time step, the network learns what should be memorized and what should be forgotten. On top of this, we add something crucial for the task, an attention mechanism, learning some importance units, alpha, weighting how much attention should be paid to each of the activations produced in the previous step. Based on these, a sentence representation, S, is calculated at every time step. On top of the attention mechanism, there is a simple layer fully connected to two output units corresponding to the sarcastic and sincere decisions. We can now train on this network and collect some results. Here are the evaluations obtained on 4 different datasets for the statistical and for the deep learning models. For comparison, we depicted in purple the performance reported by other researchers on the same datasets. As you can see, we have achieved results very close to the state of the art. More than that, we made a qualitative analysis to answer our question addressed at the beginning, namely, which portions of the context trigger the sarcastic intent. This was possible by exploiting the attention mechanism and extracting the importance units learned to understand how is the network making some decisions. In these sarcastic examples, we colored each word in proportion to its attention weight. So, in bright red, you can see the words that have received maximum attention. In general, these are sentiment-bearing words, interjections, and stereotypical topics. Note that Twitter-specific markers and even numerals are given special importance. To conclude, the essence of sarcasm lies in the contrasting emotional nuances. Due to its strong subjectivity and personal flavor, sarcasm is a form of affective expression that is not trivial to identify neither by humans nor by computers. Hopefully, with studies like this, we can bring our understanding closer to what sarcasm really is.